So here's a 4x4 matrix, and let's try to do a cofactor expansion to figure out its determinant. Finding determinants with cofactor expansions is a lot of work, but this matrix has some wonderful structure in it. This is what's called a triangular matrix. It kind of looks like a triangle. The non-zero entries are there, and that means there are a lot of zeros. And let's exploit that. So let's do a cofactor expansion along the top row because there are zeros here. I could have equally chosen the last column because there are a lot of zeros there. No matter what I do, I'm going to get the same result. So if I were to take that first entry and block out this row and this column, I'll be left with a submatrix, -1, 0, 0, 6, 3, 0, -8, 4, -3. I'm going to pick the same sort of thing to do my next cofactor expansion. I'm going to exploit the zero. So let's pick this first row and I will block out the remaining entry. Now, just a little comment, all of the other zero entries up top create a whole bunch of zeros added to this. Same thing's going to happen here. If I do a cofactor expansion on the first row of this matrix, I'll get a -1. I will have this submatrix 3, 0, 4, -3. All of the other entries corresponding to these will be 0. Finally, I'll get 4, -1, and then the 2x2 determinant 3 times -3. The other term gives me a 0. So I found the determinant. I'll get a 36. The point of the story is not the final number. It's what I notice about these entries. These values are exactly the values of the diagonal of this triangular matrix. So here's a nice little result. The determinant of a triangular matrix is the product of the diagonal entries. So that's really nice. That's a handy result. And in fact, it's so handy, it's going to actually inform everything that we do from here on in, because calculating a determinant by cofactor expansion is a lot of work. And I'm trying to find another way to do it. So our goal is going to be to try to write everything as a triangular matrix so that I can exploit this result. There's some notation here. If I have a triangular matrix, I'm going to say U11, U22, UNN. These are the diagonal entries, and let's say our matrix kind of looks like this. The determinant of that matrix is just going to be U11, U22, all the way down multiplied together. There's some math notation that you may not have seen before. This is a giant letter pi. It's a Greek letter P, stands for product. I equals 1 to n UII. And that's just another shorthand way of writing this. Let's try to make our goal to use this result to calculate the determinant of any matrix. We've already got the tools we need. So we're going to use row operations to change some matrix A into a triangular matrix. Now, there are only 3 row operations. What I need to do is figure out how those row operations affect the determinant. How does the determinant change with each one of these? Now, I'm just going to show you 2x2 examples because it's quick and it will generalize. So again, these aren't formal proofs, but I think they get the idea across. So if I give you again a 2x2 matrix, A, B, C, D, we already know its determinant is AD minus BC. So number one, if I want to do a row scaling, so let's say I take a new matrix with the first row scaled. Its determinant is just KAD minus KBC. What ends up happening is that we get K times the determinant of A. So if you do a row scaling, all that happens is that your determinant gets scaled as well by the same factor. Remember that there is an elementary matrix that performs row scaling, K001. We'll call that E. So the determinant of this matrix is just K. You can figure that out very, very quickly. We're going to use that result a little bit later. Row swapping is very easy. If I just have a matrix and I swap its rows, the determinant of this matrix, you can very simply calculate BC minus AD. That is just a negative factor of the result we had before. So it's negative determinant of A. There's an elementary matrix that does row swapping. It's just the rows of the identity swapped. So the determinant of that matrix is -1. Finally, if we do a row replacement, so let's say we have this matrix B, we don't touch the top row, but we add some multiple of it to the bottom row. you can see very easily that the determinant of that matrix, just by using the same 2x2 rule, is going to be A into D plus KB, subtract B into C plus KA. We'll end up getting the same 2x2 determinant that we had before, but we'll get KAB subtract itself. Those will cancel out. So there is no change. Row replacement is basically free. It does not affect the determinant. Now, same idea when we talk about doing the appropriate elementary matrix. This is a triangular matrix. You're not going to notice that factor of k. You'll just get a 1. If I take some elementary operation and I apply it to my matrix, it's going to turn out that it will just be the product of those two. This is either going to be a 1 if we have row replacement. It's going to be a -1 if we have a row swap. And it's going to be k if we have a row scaling by a factor of k. And moreover, now we can try to generalize. So if I give you this giant 4x4 matrix, my goal is to try to get this into a triangular form. So I'm going to find the determinant of A by using row operations. So I'm not going to do a cofactor expansion. I'm going to do row operations. I have a pivot in the top row. I like it. I'm going to try to create zeros underneath it. Now, the row operations I'm going to do here, they're just row replacement. So when I do a row replacement, there will be no change to the determinant of A. So if I do row replacements to create zeros underneath this matrix, there's going to be no change to the value of this determinant. So if I go there and I add the first row to the third row, I'll get a 0, 1, 5, 5. And if I go -3, I'll get a 0, -2, -7, and a 3. So this matrix here, you can call it U1. The determinant of U1 is just going to be the determinant of A. Now I'm going to create zeros underneath this. Once again, all I need are replacements. I'm going to take -1 bunch of 2 and add it to 3 to make the new 3. And I'm going to take 2 bunches of 2 and add it to 4 to make the new 4. There will be no change to the determinant. 1, -1, -3, 0, 0, 1, 5, 4. If I add negative bunches of this, I'll get a 0, I'll get a 0, I'll get a 0, I'll get a 1, and then 0. I'll add 2 bunches of this to get a 0. Here I'll get a 3, and then there I'll get an 11. This matrix is called U2. The determinant of U2 is equal to the determinant of my original matrix. There is no change. The last thing that I can do is a row swap. 1, -1, -3, 0, 0, 1, 5, 4, 0, 0, 3, 11, 0, 0, 0, 1. This matrix, let's call it U3. This I did a row swap. And so that means the determinant of U3 would be negative the determinant of U2, which would be negative the determinant of A. And this matrix is triangular. The determinant of U3 is just the product of the diagonal entries. 1, 1, 3, 1. 1 times 3 times 1 times 1, which is 3. And from this, the determinant of A would be negative determinant of U3, which would be -3. So this is a way that we can use row operations to calculate determinants of matrices. So we're going to build on this further to exploit other results.